Nuclear weapons are the ultimate symbol of disaster. But have you ever wondered how the US tests these devastating weapons without triggering the massive explosions that haunt our nightmares? From the days of mushroom clouds and radioactive fallout, nuclear testing has come a long way. Today, the US relies on cutting-edge methods to ensure the safety and reliability of its nukes. Join us as we uncover the secrets behind America's advanced non-explosive nuclear testing techniques, revealing a fascinating blend of science and technology. A nuclear test involves the intentional detonation of a nuclear weapon, releasing an immense amount of energy from a fission or fusion reaction. These tests can serve to make political statements or to enhance understanding of the weapon. The dawn of the nuclear age began with the Trinity test in July 1945, the first and largest atomic test ever conducted. In Alamogordo, New Mexico, the US detonated a 20-kiloton atomic bomb, creating radioactive green glass on the desert floor and leaving a 5-foot crater. The mushroom cloud soared to an astonishing 38,000 feet. Just weeks later, in August 1945, the US dropped atomic bombs on Hiroshima and Nagasaki, Japan, in a bid to end World War II, resulting in over 100,000 civilian deaths. These devastating events marked the world with an indelible lesson about the horrors of nuclear warfare. In August 1949, the Soviet Union shocked the world by detonating its first nuclear bomb. Between 1945 and the Comprehensive Nuclear Test Ban Treaty, or CTBT, in 1996, nearly 2,000 nuclear tests were conducted worldwide. The United States carried out 1,032 tests, the Soviet Union 715, France 210, China 45, and Britain 45. Since the CTBT, 10 nuclear tests have occurred. North Korea conducted tests in 2006, 2009, 2013, 2016, and 2017, while India and Pakistan each tested twice in 1998. Concerns about environmental and public health impacts halted further nuclear tests. The last tests were conducted by the USSR in 1990, China and France in 1996, and the US in 1992. This marked the beginning of a new era in nuclear policy, focusing on containment and disarmament. To gather vital information without physical testing, computer simulations play a crucial role. The advent of supercomputers like IBM's Roadrunner and Sierra revolutionized nuclear testing, enabling comprehensive research without actual explosions. The United States Stockpile Stewardship Program has advanced simulation capabilities since the end of the explosive testing in 1992. These highly efficient and precise simulations have become essential for modern nuclear testing. By December 2012, the National Nuclear Security Administration owned the world's fastest computer for nuclear weapon modeling and simulations. This technological leap allows scientists to explore complex scenarios with unprecedented accuracy on this supercomputer. Subcritical testing involves fissile materials without triggering a self-sustaining nuclear chain reaction. It's akin to taking apart a car engine to understand how it works without ever starting it. The U.S. Department of Energy conducts many subcritical nuclear weapons tests, like the Pollux test in 2012, performed underground in the Nevada test site. Using a plutonium isotope with a higher critical mass, Pu-242, these tests closely resemble real nuclear weapon triggers. Specially designed containment systems ensure no radioactive release, allowing scientists to study uranium or plutonium behavior under controlled conditions without detonating a bomb. This method provides invaluable insights while minimizing risks to the environment and public health. Hydrodynamic experiments represent another form of non-explosive testing. High-explosive detonates test assemblies that mimic the conditions of an actual nuclear weapon. By applying enough pressure and stress, non-fissile isotopes like uranium-238 and plutonium-242 behave like liquids. Computer equations based on test results and radiographs or X-ray images predict a nuclear weapon's performance. For instance, Los Alamos National Laboratory conducted the LIDA hydrodynamic experiment on August 12, 2014, at the Nevada National Security Site, using high explosives and a plutonium clone material to implode a weapon relevant geometry. These experiments are crucial for verifying the reliability of nuclear weapons without resorting to full-scale detonations. Radiographic testing is yet another method using radiation to image the interior workings of the nuclear bomb. Think of it as a nuclear X-ray. By examining these images, scientists can identify any defects or flaws in the weapon's design. This technique ensures that every component functions perfectly, providing a critical layer of quality control in the maintenance of nuclear arsenals. Ever heard of laser fusion? It's one of the most advanced and futuristic methods in nuclear research today. Imagine powerful lasers like those at the National Ignition Facility, creating conditions similar to a nuclear explosion, but without the destructive force. By focusing intense energy on a tiny target, scientists can replicate the extreme temperatures and pressures found in the heart of a star. This allows them to dive deep into the mysteries of fusion reactions in a controlled environment, without the need for actual detonation. It's like bringing a miniature sun to life in a lab. When it comes to non-explosive nuclear tests, the experimental setups are nothing short of extraordinary. Subcritical testing, for instance, is conducted deep underground, where accurate measurements and high-speed cameras capture every fine detail of the experiments. Researchers meticulously design these controlled environments to study the behavior of radioactive materials without reaching criticality. Hydrodynamic tests, on the other hand, involve the use of highly explosive materials. These tests are carried out in a large, secure facility equipped with state-of-the-art diagnostic tools. High-speed radiography systems and laser-based diagnostic techniques provide an in-depth understanding of how materials behave under extreme conditions. In all areas of nuclear testing, safety is paramount. The United States takes extensive measures to ensure the safety of these tests, prioritizing the protection of the public, employees, and the environment. Comprehensive safety protocols are in place to prevent any accidental release of radioactive materials, and to ensure that all tests are conducted within safe parameters. Specialized equipment and technology such as radiation shielding, containment buildings, and advanced filtering systems are employed to minimize health risks and environmental impact. Emergency response plans are also meticulously prepared to handle any unforeseen circumstances. These plans include specific protocols for containment, evacuation, and communication with the public and local authorities. The Comprehensive Nuclear Test Ban Treaty, or CTBT, plays a critical role in global security by banning all nuclear explosions, regardless of their yield or purpose. The verification regimen is divided into three major components. The first is the International Monitoring System, or IMS, which comprises over 300 facilities worldwide. The second component is the IDC, or International Data Center, which collects and analyzes data from the IMS. The final component is the on-site inspection process. Once the treaty is in effect, member states have the right to request inspections to gather more evidence on the ground. It's pretty mind-blowing how the US can test nukes without actually setting them off, right? This innovative approach showcases a commitment to safety and environmental protection, along with cutting-edge scientific expertise. By simulating nuclear explosions through advanced methods like laser fusion, researchers can continue to make significant advancements in nuclear science without the risks associated with traditional testing. What do you think about these innovative testing methods? Be sure to let us know in the comments below. And if you enjoyed the video, give it a thumbs up and subscribe for more.